Hello everyone, welcome to another video. Here we'll be discussing about some interview questions that are asked often in physics interviews, whether it is a PhD interview or whether it is an interview for lectureship. These questions are usually asked, and these are very basic questions. It's not like uh, these are very tough questions. They will ask you basic questions only, and according to that, uh, they will select the candidate. Okay, so first of all, there are some topics that usually are asked. For example, it's a PhD interview. Okay, so first of all, they will ask you, like, first of all, they will ask based upon your choice and which field you have given the choice, whether it is high energy physics or condensed matter physics. There are so many areas, isn't it? Or biophysics, astrophysics. Astrophysics has so many diverse subfields also. Like there is something like there is no nuclear astrophysics. Nuclear astrophysics is there. Then astrophysical relativity. There is another uh, astrophysical relativity. This is another field. So these are some very interesting fields, and from which you can choose. Okay. So according to your choice, they will ask you questions, right? But still in every whatever choice you make, there will be questions. Always there will be questions from one topic, that is quantum mechanics. Okay, quantum mechanics will have the, like, what will I say, majority of questions will be asked from quantum mechanics. Okay, because this is the basic of everything, all the research, everything is like this stems from quantum mechanics. Okay, whether it is high energy physics or condensed matter physics. Condensed matter physics they will be asking also from solid state physics, right? But still, the basic, the root will be through quantum mechanics, right? So here we'll be discussing some questions that may be asked to you in a PhD interview or a lecture interview, right? These are very theoretical questions. Here we will not be doing any numericals. See, that doesn't mean they won't ask you. You see, they won't ask you numericals. What will they ask you? They will ask you to derive something. Okay, in one of my interviews, they asked me Clave-Jordan coefficient, and Clave-Gordon coefficient. I have to derive it. Okay, on the blackboard, they will call you to the blackboard and ask to derive this. So that can be also asked. All right. So yeah, derivations can also be asked. Hmm. Another is molecular physics. That is also one interesting field of research. There are so many fields. Okay, these are just examples. Okay. Anyway, everything stems from quantum mechanics. So in this video, we'll be discussing questions from quantum mechanics that can be asked in interviews. Okay. Right. First of all, the basic question: why quantum mechanics is named as it is. So the first basic question: why? Why is quantum mechanics? Why is quantum mechanics named as it is? Okay, this is the first question in this question series. So, what will you answer this question? First, think yourself. Take your time. See, take this video as a. I know it won't. It's not like that, but you can take it as a mock interview. Okay, like not that, but you can listen to my question and try to answer. And if you can answer, that's good. That's good for you. And one thing about interviews is don't sit silent. Don't sit silently when they ask a question. Like, yeah, take your time, but always answer something else. Always answer something around the answer, or like you go to the answer You roam around the answer. Whatever you do, you answer something. That is the purpose of the interview. You have to answer something. You just cannot say that, sir, I don't know. How you don't know? Uh, because you have studied these things. So something will be there inside your mind, right? Something should be there inside your mind. So you have to take that out at that exact moment, right? So for that you need practice. You need to have discussions like this before. Okay. So why is quantum mechanics as it is named as it is? See, first of all, how did it come this concept? First of all, Albert Einstein in 1905. Okay, what he explained which phenomena? Photoelectric phenomena, right? He explained photoelectric phenomena. Okay. So, but what did he assume? He assumed that light can be absorbed in certain packets. Okay, light can be absorbed in certain packets. Okay, certain packets, and he suggested that light has an elementary quanta. It's called what? Photon. Okay, light has an elementary quanta. It's called photon. Elementary quanta. Is that alright? It was then called photon. Alright. So this contributed to the birth of a new physics in an important way, and many other quantities that were previously considered continuous, okay, continuous, were slowly discovered to be discrete or quantized. Okay, discrete or quantized. Discrete means what? What do you mean by continuous? See, continuous means suppose, okay, natural numbers are discrete or continuous. One, two, three. This is not continuous. Numbers can never be continuous because see one after one. Do you know what is it? 1.1. No, it can be 1.111 also. So it's not a continuous thing, isn't it? Right. So, but see, we know charge is quantized. Q is equal to n into e. That means it can only be a multiple of charge of electron. That is one e. It can be one e. It can be two e. It can be three e. It can be four e. So this is called what? Discrete or quantized. This is not continuous. Is it continuous? First charge is what? 1 is what? 1.6 10 to the minus 19. Second charge is 3.2 into 10 to the minus 19. So it's not 1.7 into 10 to the minus 19, is it? It's not the next number. So it's what? It's quantized. It has certain rules. It has certain values. 1e, 2e, 3e. These are quantized or discrete. This is not continuous. Okay, this is not continuous distribution. So like what? Some quantities were quantized. Thus, the emerging new physics that emerged from all this quantization and discrete things, this is called over here what? Quantum mechanics. Alright. This is why it's called quantum mechanics because here so many things were quantized. Okay, so how would you answer this question? You would start from the Einstein's photoelectric effect. So you will say in 1905, Albert Einstein explained the photoelectric phenomena by assuming what? By assuming that light can be absorbed in certain packets. Alright. He suggested that light has an elementary quanta, which is a photon. Okay. So this discovery of this thing led to the birth of a new physics. Okay, in an important way. So many of the quantities that were previously considered continuous were actually found to be or discovered to be discrete or quantized. Right? So thus, the new emerging physics stemming from all this is called your quantum mechanics or quantum physics. Is it all right? Is it all right? So this is the first question answer. Okay. Yeah. So from this exact question, the beauty of interviews is one of the very beautiful, like not beauty, but like one of the things about interviews is once you answer a question, they have the next question ready. If they have the next question ready for you, like you answer this, they will exactly ask you the next question, which they have already. That is, so you said quantum. In quantum mechanics, everything like in quantum everything has a quanta. Everything is quantized. So that is exactly the question. So the essence of quantum mechanics is that everything has a quanta. Is it really? Is it really that essence of quantum mechanics is that everything has a quanta? That's the next question. Write down the next question. Is it true? Is it really, or is it true? Or is it true that the essence of quantum mechanics, the essence of quantum mechanics is that everything has a quanta? Just think about this question first. Try to think yourself an answer. Is it really that the essence of quantum mechanics is that everything has a quanta? Is it true? Because you answered this in the previous question, so that can be again backfired at you. Right? Well, the answer is not really. It's not really that essence of quantum mechanics is that everything has a quantum. No, but in fact, it is not even true. Okay, how? For example, if we take a hydrogen atom, there is hydrogen atom. Okay, so we find that it has certain level of certain energy levels, but it is not true that energy is quantized, is it? It's not true. If we now take a different atom, okay, we find different energy levels. Different atom will be giving us different energy levels, isn't it? All right. So the actual levels does not reflect some universal property of energy, which is like what you are saying. You are saying energy, everything is a quanta. That means energy also has a quanta. No, like that's not the universal property of energy. Okay, rather it is actually specific to the system in question, isn't it? Yeah. So such things can happen in only classical physics. For example, if you have a chord, okay, so it can only vibrate at certain frequencies. However, different chords can vibrate in different sort of frequencies. Okay, so altogether in classical physics there is no natural unit of frequency, isn't it? So how would you answer this question? You will answer not really. It is in fact it is not even true. For example, if we take an hydrogen atom, so it has certain energy levels, but it is not true that the energy is quantized because different atom can have different energy levels. All right. Hmm. And the actual levels does not reflect some universal property of energy. Rather, it is specific to the system in the question. Okay. By the way, such things can happen in a classical physics. For example, you can give the example of chord. If we have a chord, it can only vibrate at certain frequencies. However, different chords can vibrate at different sort of frequencies. Okay. So in classical physics also there is no natural unit of frequency. Is that all right? So this is another question. Okay. So okay, from here again, as you answered this question, there is another question set up for this answer. So that is the thing about interviews is once you answer a question, you have to think that if I answer this, can they ask me more? So you have to be careful about that. So once you answer this question, the next question is ready for you. The next question would be after you answer this one. That will be then what is the essence of quantum mechanics? As you said, you first said everything is a quantum, but now you are refuting it yourself. You are contradicting yourself. So you are now confused then. So the interview will ask you, you are confused. You are not able to answer like properly. Say, tell me. So what is the essence of quantum mechanics then? Like what makes it so different from classical mechanics that we have to study it differently? Okay, so that's the next question then. Next question they will ask you is, then what is the essence of quantum mechanics? What makes it so different? What makes it so different from classical mechanics? Okay, this is the question. Hmm. See, in classical mechanics, there is a certainty. Quantum mechanics is defined by what? Uncertainty. We cannot say that the object is there, object is the object can be here. There is a probability. We in quantum mechanics, there is the game of probability. Everything is probable. That it is probable that the particle will be there in the box. We are not sure where the particle is. So it acts upon the concept of probability. Probability means it can be there, it can be here. So there is a certain level of uncertainty. Yeah. There is a certain level of uncertainty. So quantum mechanics takes account of what? Uncertainty present in nature. Okay. All right. So here the word uncertainty is not meant in the sense that we don't know something. Okay. It's just that we're not certain of something. We're not certain of the position of the object or momentum of the object. Okay. So actually quantum mechanics says that reality is not something crystal clear. Okay, it's not clear. It's very blurry. It's misty. Okay, so when we describe the electron's position in a hydrogen atom, there is an hydrogen atom. Okay, we're describing electron's position in an atom by a certain spherical cloud. It's like this. Okay, so electron can be anywhere here. So we don't know exactly because we're not sure. We're not sure whether it is there or not because like all right. So rather the electron itself is not sure about its position. And in some sense, it is true that both here and there and little bit and all around, it can be there. So that's why we draw the cloud around it. So that electron can be anywhere here. We don't know. We're not sure of its position. So there is a bit of uncertainty. That is what makes quantum mechanics different from classical mechanics. Right? It gives a more clear version of the reality by saying us that it's not clear. Okay? It's kind of yeah. That's what it is. Okay. Yeah. So again, as we said that quantum mechanics uses probability a lot. So the next question will be: so quantum mechanics must use probability theory. Is that what it is? So question number four. So quantum mechanics must must always use probability theory. Probability theory. Hmm. Well, yes. The answer should be what? Yes. Yes, it does. Yes, but it uses a built-in probability theory, which is actually different from the classical one. Okay, it's different from classical mechanics. It's called what, as I said, as a use the term built-in probability. All right. So there is actually a mathematical difference between probabilities arising from what lack of knowledge and intrinsic uncertainty. Here, as I said, if the electron doesn't know its own position, that is called what? Intrinsic probability. Sorry, intrinsic uncertainty. But it's very different from lack of knowledge. It's not like we don't know. We know that the electron is there somewhere, but there is a sense of uncertainty about it. That's called intrinsic uncertainty. So there is actually a different mathematical difference between probabilities arising from lack of knowledge and that from intrinsic uncertainty. Okay? So, but when we use classical probability theory, okay, so we assume that at each experimental round, each measurable quantity, okay, assumes a value which is independently from the fact that whether we have measured it or not. But in reality, at each experimental round, we can only measure some quantities, right? So it turns out that the statistics emerging from experimental data actually contradicts the assumption that at each experimental round, okay, for one, two, three, each experimental round, all quantities had a value. That like, on the other hand, probability theory. This is classical mechanics. On the other hand, probability theory in quantum mechanics actually doesn't make such assumptions. In fact, the predictions made by quantum mechanics are in perfect agreement with the what experimental data. So the point of view from what will you say? Point of view from abstract mathematics. Okay. Point of view from abstract mathematics. The main difference is that the event lattice. It's called event. Read about it. Event lattice used in classical probability theory is distributed, whereas one used by quantum mechanics is not distributed. Okay. Is that alright? So how will you answer this question? I hope you understood. This is a bit tricky one. So how will you answer? You will answer yes, sir. But it uses a built-in probability theory, which is actually different from the classical mechanics theory. There is actually mathematical difference between probabilities arising from lack of lack of knowledge and intrinsic uncertainty. When we use classical probability theory, we assume that at each experimental round, each measurable quantity assumes a value, independently from the fact that whether we have measured it or not. In reality, at each experimental round, we can only measure some quantities. Okay? Then you can answer. It turns out that like statistics emerging from experimental data actually contradicts the assumption that at each experimental round, all quantities had a value. Okay. And on the other hand, probability theory used in quantum mechanics doesn't make such assumptions. And in fact, predictions made by using quantum mechanics are in perfect agreement with experimental data. Okay? So, from the point of view of abstract mathematics, okay, the main difference is that the event lattice used in classical mechanics is distributed, whereas in quantum mechanics it's not distributed. Okay, that should be the answer. It's a bit tricky one, I know, but you should read about it. Read about it more. Okay. Okay. Next question will be, we'll slowly go into the that quantum mechanics. That is, what is the wave particle duality? We hear about it a lot in quantum mechanics. So, what is it? Can you explain about it a bit? What is wave? Sorry, what is the question number five? What is wave particle wave duality or wave particle duality, whatever? Okay. So, what is particle wave? Again, particle wave. At one point, it can be a particle, it can be a wave. So, this is just another example of what? Uncertainty, isn't it? Probability, uncertainty. Uncertainty, again, like consider light. Okay, light. So, it can be emitted and absorbed in certain units. So, this is what, like, I've been suggested from what? Photon theory. It can be absorbed, it can be emitted. Yet, like, from the classical point of view, the situation is that a particle can sometimes behave like a wave. Okay, a particle can sometimes behave like a. This is a classical point of view, but from quantum mechanics point of view, like the particle is a particle, but the position is uncertain. Okay, and it can be both here and there a little bit. So, that thing, so that uncertainty of the particle, that it can be here, it can be there. So that leads to which kind of thing? That means even a single particle can produce what? Interference pattern. If you do Young's double slit experiment, okay, experiment. So what does it say? If you just read about it, okay, this is a work. You read about it and connect it to what? Particle wave duality. Okay, is it all right? Yeah, this is a work. Next question is, okay, there is a very basic question we never ask ourselves also, that like we consider so many waves like photons, light waves, but why not sound waves? Why not sound waves? Like the question will be, okay, the question will be, why is it that sound waves are not normally considered, not normally considered as having as having particle like properties, because it's a wave. So why cannot why can it not have particle like properties? Or suppose there are raindrops, why we don't say that they have wave like properties? Why they don't have wave like properties? The thing about interviews is sometimes they ask you questions that make you question about your question making ability, like why you couldn't ask that question while you were studying, right? So yeah. So again, a very, this question may sound stupid, but it has logic. Why sound waves cannot have particular properties? Because it's a wave. You were saying in the previous thing, that previous answer, that everything has a particle wave duality. And what about sound wave? Sound wave doesn't have particle property. And what about raindrops? Raindrops don't have wave-like property. So what is it? What's the mystery behind it? Think a bit first. Think about it. You can pause the video if you want. See, what is the wavelength of a wave? Wavelength is what? H by P. That is H by mv. H by momentum, right? So sound waves, their wavelength is too long. Wavelength is too long for sound waves. Okay, too long for sound waves. Is that alright? Too long for sound waves. Hmm. So their wavelength is too long. Hence, the sound particles have too little momentum to exhibit particle properties, isn't it? See, lambda is too long, too big, and your, if you see h by mv, so lambda is inverse proportional to v. That means v is inverse proportional to lambda. That means if lambda is too big, then v is too small. So if v is too small, then how can it exhibit your particle properties? Okay. So the velocity, you can answer velocity or momentum. Okay. So becomes too small. Momentum is too small for sound wave to show or to exhibit particle-like properties. Okay. How will you start the answer? You will start the answer as wavelength of sound is very high. So that lambda is equal to h by p. So p is inverse proportional to lambda. So momentum becomes smaller. Okay. So momentum is too small for sound wave to exhibit particle-like properties. Okay. This is the sound wave is gone. Now what about your raindrops? For raindrops, raindrops have what? A large mass. You can see. This is mass is there also. Raindrops are large, like comparatively it has larger mass, right? So again, inverse proportional to mass, mass is greater, so lambda will be very small. So again, raindrops don't have that wavelength to show wave-like properties. It is too short. Okay, to undergo any significant wave-like property, whether it is diffraction or anything else. Okay, yeah. Why? Because diffraction. You can write one point. Diffraction can only be observable. Can only be observable if the dimension of the aperture, dimension if the dimension of the aperture aperture is comparable to the wavelength of the wave. The wavelength of the wave. Is it alright? So again, this wavelength is not even comparable to the wavelength of the wave. Sorry, this dimension of the aperture is not even comparable to the wavelength of the wave, which is very small because of the larger mass of the raindrop. Is it alright? Is it clear? I hope it's clear. Okay, you can so all of this started from photoelectric effect, right? Isn't it? So they can ask you one question here. Question number 7 can be, uh, what are the four results of the photoelectric effect experiments? Okay. So what are the four results of the photoelectric effect experiment? What are the four results? First result is current is proportional to intensity. Intensity of incident radiation. How is it? Because more the intensity, more number of electrons will be emitted from the surface. More the number of electrons emitted, more will be the current. I is equal to what? Q by T. Ne by T. So more number of electrons will give rise to more number of more current. So current is proportional to intensity. Okay. And this can be also explained using wave nature and particular nature of light. Okay. Next point, what is the second result of the photoelectric effect experiment? So for every material of cathode irradiated, there is a threshold frequency. There is a thing called threshold frequency below which what below which if the incident radiation has that frequency below threshold frequency, then there will be no electrons emitted. So this is the minimum frequency of the incident radiation for which electrons will be ejected out of the metal surface. Okay, is that all right? Now, third point was maximum kinetic energy, Ke max. Maximum kinetic energy, okay, of the emitted photoelectrons depends only on frequency of incident radiation. Frequency of incident radiation, because Ke max incident radiation. Remember that incident Ke max is equal to h nu minus h nu naught, because h nu naught is constant. This is work function. Work function of a metal is constant. Okay, it's just that h nu is what? So it depends only on nu. Hmm. Yeah. The number fourth is emission of photoelectrons. Okay, starts with no observable time lag. There is no time lag. It just starts immediately, spontaneously. Even for very low intensity of incident radiation, it is a spontaneous process. Okay, there is no time lag between two emissions. Right. Yeah. Okay, one more question we'll do. One more question. This is the last one. This is also usually asked in interviews. That is, what is a black body? What is a black body, and what are its characteristics? What are its characteristics? Okay. So first of all, tell me what is a black body? What is a perfect black body? Black. Black does what? User general knowledge. What does black do? It absorbs the radiation. Okay, doesn't it? That's why you are advised not to wear black in summer. But this is also one same, but there is a bit of difference. What is a perfect black body? A perfect black body. What is it? It absorbs the radiation completely, and whatever it absorbs, it emits it completely. So there is nothing left. Okay, complete absorption and complete emission. All right. So you can write a perfect black body is the one which absorbs and emits, which absorbs and emits radiation completely. Okay, but in reality, there is no perfect black body. Okay, we have to coat the black color over the surface to make a black body. There is no perfect black body. Black body is also said to be a perfect observer. Okay, because it absorbs all the wavelength, absorbs all the wavelengths of the incident radiation of incident radiation, right? And the black body is a perfect radiator also, because it radiates the entire wavelength absorbed by it. Whatever wavelength it got, it emits it. So this phenomenon is called a what? Black body radiation. So there is so much to black body radiation. Please read about it. Okay, this is a very important phenomena in the context of quantum mechanics. Okay, so I hope you read it properly. Okay, then we will be discussing more questions in the next session. Thank you for watching.